Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at a foundation to an introduction of what exactly is chemical engineering. Now we're going to take a look at what you need to be doing and what you need to be focusing on to be a successful chemical engineer. We'll take a look at a mock couple of lectures, both in reactor design and fluid dynamics and mechanics. And then I'll show you some places that you can find useful resources and also a bonus content at the very end of this video. So be sure to watch all the way through to the end. So the first question would be, what is chemical engineering? Then according to the Oxford English Dictionary, chemical engineering is the branch of engineering concerned with the design and operation of industrial chemical plants. Now, when that is relatively true, it is quite restrictive because chemical engineering is a lot more. Now, to be more specific, chemical engineers essentially take raw materials, we devise a process in order to produce new products. We're also responsible for optimization, implementation, and the running of a process. Now, we could even go further and talk about the decommissioning of a process, the recycling, renewables, all that sort of stuff. So you can see that the general definition of a chemical engineer isn't actually a proper representation of what chemical engineering actually is. Now, to give you some perspective here, now this value remains between 95 and 98%, but around 95% of everything that we use on a daily basis, anything you enjoy from mobile phones to cars to your TV to books to anything that you can think of, has been through the hands of a chemical engineer. Now, I don't necessarily mean literal hands, but this can be in the form of the design of a manufacturing plant, the design of the process, the design of the equipment, the reaction that is involved in order to produce the thing that we're talking about. So chemical engineers are pretty much involved in absolutely everything. Now, a question that I often get asked by prospective students or current students is chemical engineering hard? And essentially, in a nutshell, the answer here is yes, but it is for good reason. Chemical engineering is voted the third hardest degree to achieve in the world. And in some countries like the UK, it can often be deemed as the most difficult. So don't let the fact that chemical engineering is hard put you off, because chemical engineering is a very, very rewarding degree, both financially and intellectually. But let's consider what chemical engineering actually involves. Now, this is just in a general sense. But we have things like maths, we have physics, it even involves chemistry, we have different processes, fluid mechanics and dynamics, mechanical engineering design principles, we design process and safeties, reaction engineering, biochemistry and bioprocessing. We even go into business and accountancy skills and fundamentals. So sometimes you'll find that in business, a lot of directors and CEOs of companies and universities are from a chemical engineering background. Now, mass transfer and heat transfer principles are core to a lot of chemical engineering, and all of these kind of encompass in unit operations. And just a rough idea as to the percent that each of these encompass, you'll see that chemical engineering analysis and design constitutes probably the bulk of what you'll be doing as a chemical engineer. And you can see that there is some chemistry, there's some maths, we have written and oral communication, because obviously, you have presentations, you will have dissertations, reports, etc. So again, you will find that it looks overwhelming, but you always go through it in university in small chunks. So you don't have to do this all at once. You take it step by step, and eventually you will become highly competent in all these areas. So what can you expect from chemical engineering? So this is something that, for me, I wish I had a better understanding before I actually became a chemical engineer. So My undergraduate degree is in chemical engineering, my postgraduate master's degree is also in chemical engineering, and my PhD is also in chemical engineering. So it's safe to say I have done chemical engineering for a very, very long time. And now I've just started a couple of businesses that involve chemical engineering, and I'm also now a lecturer. But when I started, I hadn't a clue what chemical engineering actually was. All I knew is that it combined maths, chemistry, and it made a lot of money. But there is a lot more to it than you might expect. So the first and foremost is whatever volume of chemistry you expect, half that right away. There isn't as much chemistry as you might expect. On the contrary, whatever level of mathematics you expect, don't double it, triple it. Because maths is in absolutely every element of chemical engineering, of any engineering discipline. So there is no escaping that maths will be either your friend or your enemy throughout the entire process. So make sure the one thing, if you're a high school leaver or you're just starting out at university or college, make sure that you are highly competent in maths. Now, the first 2 years are essentially the building a foundation of the maths, the chemistry, the physics, and the basic engineering principles. All of these will be core in order to actually begin to learn chemical engineering. Because surprisingly, you'll find that to actually get into chemical engineering modules, you really need to start in your third year. Granted, sometimes in second year, depending on what institute you go to, you might get a taster of some chemical engineering modules, but predominantly you'll be looking at fundamental maths, chemistry and physics. Now again, depending on your high school grades or your experience, the first 2 years will either be a breeze or a challenge. But regardless of the route, you need to ensure that whatever you learn in these 2 years, you really know it inside out. Because these are going to be fundamental when you look at the hardcore aspect of chemical engineering. You want to be able to put in your time to the chemical engineering fundamentals rather than still struggling with the maths or the chemistry. Now, the most important modules. Now, this is a very difficult question to answer because it depends on what you are interested in. And there is a lot of different modules in chemical engineering. But in a nutshell, in order to basically get a better idea, some of these modules are what we'd class as just noise to the overall objective of being a chemical engineer. So it just means that they have to be done, they might be small credit modules, but they have to be taught. They might not necessarily be useful. But as a general rule, what I would recommend you to focus on and pay particular attention to would be material and energy balances, reaction engineering, because that in itself is what distinguishes chemical engineers from any other engineering. Distillation design. Distillation is a huge module in chemical engineering. It spans all years and it can get incredibly complicated. Fluid dynamics and mechanics. If I was to summarise what a chemical engineer does, I would say it works with fluids, because almost 90% of the systems that we use involve some form of fluid. Mass and heat transfer, these are precursors to all these other principles. Thermodynamics. Thermodynamics plays a part in pretty much all of fluid dynamics, heat transfer and mass transfer. And then making sure that you know your stuff when it comes to CFD, HYSYS and CAD. So again, we have multiple different courses on these, both free and paid. So I'll put a link in the description to these and you can check them out when you get a chance. Now let's take a rough idea. Now we're not going to go through an entire lecture because that would mean this video would be massive. But just to give you a very, very brief idea of the difference between one module and another, will let you see the variation in what you will have to learn. Now, I says that at the beginning it was reactor design, but this can fall into reactor design, but we're going to call it material balances. Right, but these two are kind of integral, especially in the design phase. So material balance, also known as a mass balance, is essentially the preliminary stage of designing any piece or process. Alright, so when we talk about a piece of equipment, we can refer to a reactor. Now we use what's called the general material balance formula. And this is based on a set of design assumptions. We can remove specific terms where appropriate. Now the general formula is that accumulation equals the input minus the output, plus or minus the generation, plus or minus transfer. Now each of these encompasses a different principle. So accumulation assumes that we have less coming out than we have coming in. So we have an accumulation of material. An input and an output would mean we have a continuous system. If we have a batch system, we don't have an input and we don't have an output. Generation can be the generation of heat. So we produce heat or we absorb heat. And the transfer, we can sometimes call that work and energy balances, or we can have the transfer of mass. But we can also sometimes state this in terms of energy as well. It just depends on the type of system that we're using. Now we're not going to go deep into the material balance content because we have an entire course on material balances, mass and energy balances. That's such an integral course and a part of the fundamentals of chemical engineering. But all we're going to do here is I'm going to just focus on the accumulation term. Alright, just to show you that on the face of it, it looks fairly simple, but it can just grow arms and legs so quickly. So taking the accumulation, we can express accumulation in three different ways. We have accumulation can be the rate of change of mass with respect to time. Now for the mathematicians and the beading-eyed chemical engineers, you will notice that these are differential equations. So this is where maths plays a part. So the rate of change of mass with respect to time can be expressed as dm over dt. We can also express this as a change in the volume with respect to time. So that would be dv by dt. And then we can have a change in the liquid height with respect to time. So dh by dt. Now the question here is, do you notice a recurring theme here? And the answer should be yes, because the accumulation term is a rate of change. So right away in mathematics, you should be thinking calculus, differentiation, integration. Now what you'll also notice is that the accumulation term, because it is a rate of change, regardless of what we have as the numerator variable, the denominator is always dt. It's always with respect to time. So it's the change of these different parameters when time moves on. Now, looking at an idea on fluid dynamics, just to see the difference in the material and how it would be delivered, then fluid dynamics and mechanics can be challenging, but it is very, very interesting, at least for me. And most applications will involve fluids at some point within the system. Now, if you're going to be a chemical engineer, you must know this formula. And you need to know exactly what its purpose is. Now, this is just one of several different formulas. But the formula here is that Re equals, now this is rho Vd over mu. Now, ask yourself the question, what is this formula? And your answer should be Reynolds number. Reynolds number should be etched onto your bedroom wall. It should be etched on everything you look at. In fact, I wouldn't advise it, but if you ever forget it, even get a tattoo of Reynolds number. But I don't advise to start tattooing yourself with engineering principle equations. But nonetheless, this is an incredibly important formula. And what this essentially does is this tells us a criteria for the type of flow that we're going to have. Are we going to have turbulent flow or are we going to have laminar flow? Because as soon as we distinguish which one is turbulent and which one is laminar, all the design equations will be different. Because laminar flow behaves much differently to turbulent flow. Now, I could go on for days about this type of stuff, but I'm not going to bore you with all the details. I got into copious amounts of detail on our fluid dynamics and Mechanics course. So again, I'll put a link in the description to all these so that you can check them out and have a look at the free stuff and see what you think. Now, another thing on the fluid dynamics is we can create these velocity profiles. Now, depending on the type of fluid that we have, these types of systems will actually change. And we'll see that in the next slide. But essentially what we can do is we can model different fluids and show what their velocity profile within a pipe actually looks like, which is incredibly important. And it's very, very useful for understanding how these systems actually interact. We can model every single part of this, this curve. And one of the very cool things about this is there's actually a thing here. So right at the very edge, so right at the wall of the pipe, we have a thing which is called the no-slip velocity. And what that means is that the fluid just adjacent to the pipe wall actually has a velocity of 0. So we actually assume that the velocity here is 0. So that's incredibly, incredibly interesting, especially for me. It might not be necessarily for you, but it's a very, very cool way of looking at things in a slightly different perspective. Now, as I said previously, believe it or not, there is more than one type of fluid. And we actually have several different types. So the one that we are most common with is non-Newtonian and Newtonian fluids. That should be, right away, you should be either recognise non-Newtonian and Newtonian fluids. But here we have things called the Bingham fluids, we have shear thinning fluids, known as thixotropic, we have shear thickening fluids, we even have what's called a Herschel-Berkeley fluid. So there is tons of different fluids, and it's based on this plot against shear stress and the shear rate. Because what this tells us is that the gradient of this line, of all of these lines, is the viscosity. So in essence, what we can say here is a Newtonian fluid has a constant viscosity, i.e. its viscosity won't change no matter how much shear rate or shear stress we apply. Whereas things like the Bingham fluid, that requires a significant amount of shear stress before the viscosity will actually start to change. Now, the behaviour is highly influential on their respective applications, because imagine we have a shear thickening fluid. So that means that as we apply a shear, so that means we push it through a pipe, or we put it through an engine and we cause friction. Then that friction acts as a shear stress. The higher the shear rate, as you can see here, we increase the shear rate, the gradient or the viscosity increases significantly. So we wouldn't want a shear thickening fluid to be the oil that we put in our car engines, because what would end up happening is the fluid would get so thick that the engine would stop working. So what we want is things like shear thinning fluids. We want potentially Newtonian fluids, but the ideal one being is a shear thinning fluid, because we want it to be very, very low viscosities. Now, as chemical engineers, we need to know the characteristics and the modelling equations of all these different types of fluids. And it sounds daunting, but it is actually very, very straightforward once you get your head around the distinction between Newtonian and non-Newtonian fluids. So, the question here is, now that we've had a look at all that, and we now know the fundamentals what's required for us as chemical engineers, how do we get the help and support and advice when you need it? Because that's ultimately the goal here, is how can you get the help, support and advice along your chemical engineering journey? Well, there's a lot of different places. Some that are good, but a lot of them are very, very bad. And you just need to be very careful, because when you're starting out, it's very difficult for you to be able to spot, and for a lack of a better word, the bullshit without all the internet information. So finding reputable sources online or within your university are going to be key. That's your starting points. So when you go into things like Wikipedia, when you go into things like random news websites, stay clear of the information because it is unvetted. We don't actually know who's actually written it. It could be correct, but there is no way, especially to begin with, for you to know which is, what one is correct and which one is wrong. So for example, if you were reading a passage about the Reynolds numbers and a statement said that the Reynolds number of 10 million equals a laminar flow, then right away you should be going, that is complete and utter nonsense. Alright, you would stay clear of that because Reynolds number should be anything between 2,300 and 2,500. Anything lower than that, that is a laminar flow. Now make sure that your material is compliant with the IChemE. Now the IChemE is the Institute for Chemical Engineers, and those are the governing body for every chemical engineer on the planet. And this ensures that if it is IChemE compliant, then the material will be up to date, and it ensures that everything that you are learning is relevant to your degree and actually worth your time, because there is no point in studying something that isn't going to be worth the time or the paper that it is written on. Now also consider things like extracurricular events at your university. Maybe some online courses, free and paid. Maybe find a mentor, take some free quizzes, or even join Facebook groups, social media groups, go onto YouTube. So that's probably the best places to find support when you need it. But that can take a lengthy process, especially to try and vet where the best places to go. Now, just for anybody that is new to the channel, just a quick introduction and exit. But one of the things that for support, guidance and advice, I would of course recommend the ChemEng Student. And this is founded by myself. My name is Dr. Callum Russell. And I founded this company on the sole purpose of fulfilling every point that I just mentioned in the previous slide. Because now we've been trading for about a year and we are now a global established business. We collaborate with several different universities and companies around the world, which is just insane. We provide the most up-to-date and IChemE regulated lectures and tutorials. I mean, we have thousands of questions and solutions, typed solutions. So it's super, super easy to find what you're looking for and get a complete comprehensive explanation. And that's what you need when you're studying chemical engineering. But the key thing here is that it is IChemE regulated, which means that it will be the material that you use at your university. Now, we don't just offer courses, okay? We offer free and paid courses. But what we're also introducing is a mentorship program, whereby students that need additional ongoing support for things like exam preparation, for coursework, for advice, for help, and just a friendly face, is we're offering a mentorship program. We also have exam preparation support. So when you're getting ready for your exams, we can go through the type of content, we can show you the hints, we can show you the tips, all that kind of stuff. And then one of my personal favourites is the free quizzes. I absolutely love the free quizzes. And we also have one that has a monthly prize giveaway. It's great to see lecturers and students, and sometimes the students do even better than the lecturers. It's a very cool way of just testing out your ability and where you need to work on. It's great, it's free. I'll put a link in the description to that and you can let me know how you get on. But as a thank you for getting to the end of this video and for your time, because everybody's time is very valuable, so I thank you very much for giving me your time, is that what I'm going to give you is a 10% off your first course. So use the coupon code WELCOME10%, and we hopefully will see you in one of our courses. But please do get in touch. We love to speak to as many different students as possible from all around the world. It is great. So please do feel free to get in touch, even just for a conversation, if you want to learn more. or whatever it is that you want, we will try and fulfill that need. So thanks for watching. Hopefully this gave you a better idea on the fundamentals and what you need to be a successful chemical engineer. Hopefully this gave you some guidance and you've seen the value in this. If you liked this video, please like, subscribe, and please subscribe to the channel because it really helps us reach as many chemical engineering students as possible. So thank you for your time, and we hope to see you in another video.